Good morning. I am amazed that the space community came so far. We are able to build a bunch of satellites in different countries in Europe, put it on top of inside an orbital deployer that is made in the United States, put it on top of a rocket, created in Europe in many countries, and then we are able to launch it from a facility in South America. It is not so in every scientific discipline. Yesterday I was trying to modify my presentation, and I've learned that it is not always true that you can connect a plug of a laptop built in Poland or bought in Poland to an electrical socket in Switzerland. So maybe later on we can do something about it. When I started to be interested in space, I was one of the first in my university, and I was certainly the first one in my department. While being a pioneer is exciting, that's a challenging thing to do, it also has some downsides. I've learned that, not surprisingly, the university is not willing to pay tens of thousands of dollars for software just because one student wants to learn how to use it. Fortunately, thanks to international cooperation, I had the opportunity to learn a thing or two about space or space software. And later on I decided to contribute and I set out a humble quest to do something about it. And that's how the aerospace block set for XCOS was born. Today I want to tell you what it is, how does it work, what can it do for you, how you can get it, and can you contribute to it. First of all, I would like to say that Aerospace Block Set for XCOS is an open source tool, so it's free for all of you. You can download it today and check it out. And I wanted to create a tool for CubeSat community that is highly configurable, that is not tied to a specific mission, that allows you to make a space simulation that you want to do. And the usual way to do that is by writing a computer program. And I've learned that there are at least two ways of writing computer programs. First of them is classical programming. This is a very simple computer program I wrote that does the very simple orbital simulation. It simulates a satellite on a certain orbit, and then it plots its trajectory over a map of the Earth. It is apparent that it's not immediately obvious what it does, and apart from being able to understand orbital dynamics, you also have to know how to program, and you have to know the underlying libraries. There is, however, a second way of writing computer programs, and it's sometimes called diagrammatic programming. If any one of you is familiar with Simulink, you know what I'm talking about. So this is the same program, doing the same thing, written in aerospace block set. I will explain it. First, to simulate satellite orbit, you need to know the orbit in the beginning. And this is done in many ways. Typically in this case, we are just giving it Keplerian elements of the orbit in the initial time. We also have to say when the initial time is, so it's called the epoch. And we also have a block that allows to configure how the time flows during the simulation. The arrows in the diagram represent the data flow. So all the data that are manually inputted in those three blocks can be then fed to a next block that actually performs the orbital simulation. It is triggered by another block that is able to configure how often the simulation will recalculate the orbit. Then, as you may know, Keplerian elements are not a very intuitive way of explaining where the satellite is at the moment. And there is a block to convert it to Keplerian, to Cartesian coordinates that we all love and we all know from probably primary school. Then there is another effect that we should take into account. So far we've simulated satellite moving around the orbit, but we have to take into account that at the same time Earth is spinning underneath. So we convert from Earth-centered inertial frame to Earth-centered fixed frame because we want to plot the trajectory on Earth map. Plotting itself is done by another block, and if we want, as we often do, save the data to use it later on in a different context, we can also do it with another type of block. I hope it is more clear to program in this way. I hope this has also educational flavor to it, because it is very easy to explain what is happening. So we don't only input parameters of the simulation, click button, go, and get the result, but it's also very easy to understand what's actually doing, what the program is actually doing. All this is possible because of Scilab. Those of you who are familiar with MATLAB will immediately know how it works, because Scilab is open source equivalent for MATLAB. And it has a module called Xcos, which is equivalent to Simulink. While Scilab allows you and provides you with multiple libraries to program in a classical way, Xcos allows you to program in a diagram, and it provides various simple blocks that allow you to perform basic mathematical transformations. The neat thing about Scilab Xcos environment is that you can write your own modules. And there is, in Scilab, there is a great module called Celeste Lab, which is developed by CNES, the French Space Agency. It is also open source, you can download it today, and it is a very sophisticated tool, a very capable tool to perform orbital aerospace simulation. And I'm using that to implement diagrammatic programming in Xcos. This gives me quite good degree of certainty that those simulations we made are very precise, and they are validated by CNES against commercial software. So Aerospace Blockset is actively developed since 2011. Just this week, it reached over 9,000 downloads. It is available for Linux, Windows, and Mac, and currently contains 49 functional blocks. All those blocks are automatically tested to ensure the high quality. They are documented, and there are a few examples provided. I don't want to go into details, but those are some of the Aerospace Blockset features. You are able to perform basic algebraic operations that you may need in attitude dynamics. There are it is supporting quaternions, direction cosine matrix, and Euler angle and axis. It is possible to calculate various time representations that you may need. There are math operations. It is possible to visualize your outputs, to plot ground tracks, to plot Apollo style indicators that are red, green, or yellow. It is possible to visualize time intervals and plot azimuth elevation plots of ground station passes. It is of course possible to convert between various reference frames, and it contains a lot of environmental models, such as simple model of solar pressure, solar radiation pressure, atmospheric drag, algebraic model of Earth magnetic field, model of planet movement, sun movement, moon movement, model of atmospheric pressure density and average temperature. It is of course possible to perform orbital propagation. There are 3 propagators implemented. Just to give you an idea, I've implemented an example when the triad attitude estimation algorithm estimates attitude based on 2 vector measurements that are subjected to noise, and you can generate a plot of angular attitude error. On the vertical axis you can see the error itself in degrees, and on the horizontal axis time of the simulation in seconds. Another thing you could do is, as I mentioned before, simulate satellite orbit and plot it on top of the Earth map. You can also calculate ground station access times. In this example for Kourou and Canaveral Space Center, you can notice that on the horizontal axis there is time in minutes since the start of simulation, but you can also configure your program to show time in Julian days or show the time in hour and minutes of the day. The aerospace block set allows you to perform simulations that are taking into account the current time, so you can simulate the current position of a satellite that can make you help you with your ground station operations. You can calculate if the satellite is visible by the ground station. You can show it on the azimuth elevation plot. You can check if the satellite is in sunlight currently, so forth and so on. Yesterday I had an idea to check how far away is Mars from the Earth. And I did that simulation, making that simulation took me about 5 minutes. And at time 0, the time my presentation started, Mars was about 241,075,000 kilometers from Earth. And by the time I'm finished, it will be about 7,000 kilometers further. So if you want to send CubeSat to Mars, we should get on. I would like to thank guys that developed Celestab. That is very good environment, very good library. If you do not know it, you should definitely check it out. I would like to thank Scilab, which creates platform that makes it all possible. And I would also want to thank 2 institutions that funded developing of aerospace block set. Company you may know, Google, has an initiative called Google Summer of Code. And a second institution you may also be familiar with, ESA, also has a similar program. I would also like to thank ESA and Swiss Space Systems for allowing me to be here by granting me scholarships. If there are any questions, I will be happy to answer. You can see you can install aerospace block set in a way that is described on the web page I show you. You can find aerospace block set there. I'm happy to give you a short demo during coffee break. And if you install aerospace block set and for whatever reason you think it's not good enough, please tell me why, because I do not know what can I fix sometimes, and this feedback is very helpful. Also, if you want to help with development, develop your own features, you are welcome to do so. Thank you.
So we have a minute for questions. Are there any questions on this paper? Yeah, Eric?
Do you have any type of pointing features in the code? For example, like, do you know where your sun vector is? Do you know the orientation of satellite or anything like that? Can you?
Yes, you can calculate sun vector and magnetic field vector, and if you want Mars direction vector at a certain point of space and time. Yeah.
So I had a question. Is there a tool in the block set that you can use to do power analysis through the orbit if you know the attitude of the spacecraft and the collecting area?
Do what? Excuse me.
Do the power analysis, so you know the sun vector and you have a solar panel and you know the efficiency. Can you basically create a power curve as a function of position and attitude?
Okay. The block set has, and the Xcode itself has probably most of the mathematical functions you need. You would have to make a diagram that does that. So the things that you will be helped with, you will be able to have a block that instantly calculates sun position. You will have a block that calculates your satellite position. You will have a block that calculates if the satellite is in sunlight, so Earth eclipse. And as for solar panel efficiencies, you would have to create your own model as you would do it in Simulink.
Okay, great. Thank you very much.
Thank you.